Start from something I owe you. So to remind you, last time we were computing the energy of a free energy of a domain wall between a region with normal metal plus magnetic field and superconductor, okay, where this coordinate is x, and then we define the f to be psi over the square root of rho naught. So this is like a dimensionless field. Eta is x over lambda, the penetration depth. This is a dimensionless coordinate. A is the field is basically A over hc lambda, and B is B is B over hc in these definitions. And we chose a gauge. In this case, we can choose a gauge, this kind of London gauge, where okay, let's write it this, like A is basically the vector is A of eta in the y direction, and psi is equal to psi of eta. In this case, we found that this G tilde, the energy associated with this domain wall, is lambda over L, mu squared over 2v naught squared. The integral from minus L over 2 to L over 2. This is energy density. This is the condensate energy. This is dimensionless. And the integral gives us length. So and remember that this is like an area. So we basically get energy per unit area. This is what we're computing. It's called surface tension. So the surface tension in this case is 2 over kappa squared f prime squared plus a squared f squared minus 2f squared plus f to the fourth plus a prime minus 1 squared. Okay, and from here we got saddle point equations. Which are f double prime equals kappa squared 1/2 a squared minus 1 times f plus f cubed, and a double prime equals af squared. We saw that we can combine these two saddle point equations to derive a constant of motion, which is 2 over kappa squared f prime squared plus 2 minus a squared f squared minus f to the fourth plus a prime squared equals to 1. Okay? And then using this constant of motion, we can inject it back into the surface integral, which means, so it's important to note that there is a difference between this expression and these expressions here. Okay? This is basically free energy. In this case, it's a generalized, it's like a Gibbs free energy, which is which accounts for the energy of any configuration. These are saddle point equations. They're the ones that minimize this free energy. Okay, so this is a difference between these two. And this is correct only at the saddle point. Now we inject this back in here, and then we found the following relation, that on the saddle point, G tilde is equal to lambda over L, mu squared over 2v naught, same integral d eta, and then we had 4 over kappa squared, f prime squared, plus 2a prime, a prime minus 1. But this is also equal to lambda over L, mu squared over 2v naught, the same integral d eta, a prime minus 1 squared minus f to the fourth. Okay? Now we use the first expression to show that when kappa is greater than 1, then G tilde is negative, and if kappa is smaller than 1, then G tilde is positive. Okay, so somewhere in between it must cross. Okay, and the place where I made the mistake was when kappa is 1 over square root of 2. Okay, and here I פישלתי קצת, as they say. So let me correct myself just for completeness. So the logic is going to be this. We're going to assume that G tilde is equal to 0, which means that there is no surface tension. It's exactly the point where it basically crosses between having vortices and not having vortices. And then we're going to show that this is consistent. Okay? And how are we going to do this? Let's assume, okay, so we're looking at this case. Assume, yes.
Is this saying that we have equilibrium in the phase transition or something like that?
First of all, we can assume that we have equilibrium in the phase transition regardless. What do you mean by that? Can you explain the question?
We have like the same value of G. Like we have the value when we cross the minus.
By the way, I forgot to mention that here H is equal to HC is equal to square root of 4 pi mu squared over V naught. So this is a special case where we have this exact magnetic field. Yes, so what is the question?
So we have so we have this equilibrium between the phases that it doesn't prefer anything like creating vortices or not creating vortices. Something like that?
Well, indeed. So the point is this. First of all, we are, because we're at 8 at the critical field, it implies that the energy of having a magnetic field or a superconductor is the same. Okay? Now what we're looking at is what happens if I create a perturbation. Okay, I come with a finger and I press on the domain wall, whether there is tension to force it back in or not. So the surface tension. When G tilde is exactly equal to 0, it means that basically it doesn't matter. So you could think about it like plastically, like it just comes and it just stays. It won't care. Okay? In other cases, it will either become extremely unstable and start creating a lot of bubbles. Okay? Or in this case, it will push back. This is the physics. Okay, so the logic is this. So let's assume that this thing is equal to 0, meaning that a prime minus 1 is equal to minus f squared. So if we assume this, then this is definitely true. Okay? And then G tilde is definitely 0. Okay? So let's assume that good. Now take the constant of motion at kappa equal to 1 over square root of 2 with this value of a prime. So, or f squared, it doesn't matter. But basically I'm going to, a prime is equal to 1 minus f squared. Okay? So I'm going to plug this equation into this. So I'm talking about this constant of motion. Okay? So here I'm going to have 4. Instead of 2 over kappa squared, I'm going to have 4. Okay? So in this case, what you'll find is you'll find 4f prime squared plus 2 minus a squared f squared minus f to the 4th plus a prime squared equals 1. And then when we plug this in, so imagine that instead of a prime squared, I put this. Then you'll see that a lot of terms here cancel, and you find the equation f prime equals to 1/2 a times f. This is the condition. Now this is going to be enough for us to prove that in this case we have consistency. How? How do we do this? We're going to combine this equation with this equation. Okay? And then okay, what am I going to show? Oh, sorry. Sorry, not this equation. Hold on, not this equation. This equation. So I'm going to use this equation and this equation to show that a double prime, so I can compute it, a double prime, I can move this to the other side. Or basically, maybe actually focus on this equation. They're the same equation, it's just, it's more convenient to look here. I take a double prime, so a double prime is equal to minus 2f prime f. On the other hand, I can write that a times 1 minus a prime, where I'll take a from here, and 1 minus a prime I'll take from here. I will get that this is also equal to f prime f, 2 minus 2f prime f. Okay? So this implies if I sum up, what I conclude from these two equations is that if g tilde is equal to 0, then a double prime equals a times 1 minus a prime. But the point is that we can actually arrive at this equation independently, and I'll tell you how. All we need to do is use this equation, okay, and what else? Second, a double prime f, and so I'm going to use this equation and this equation. Okay, so if I use these two equations, I reach the same conclusion. So let's call this, say, 1 and this 2. I can say, on the other hand, this relation is also consistent with equation 1 through equation 2. So if I plug in 2 in 1, I also find that this is consistent. So what does this tell me? It tells me that when kappa is equal to 1 over square root of 1/2, this constant is like this, and I get this relation, then I get this equation. But also, if I assume that this is equal to 0, then I get the same equation from the equation, the saddle point equation. So, and I can show it. So all you need to do is just plug this in. You get A double prime is equal to A times 1 minus A prime, which is the same equation. Okay, so that's how you show that it vanishes at kappa equal to 2. Now, what does all this mean? What is the consequence? So, the consequence is that we have two distinct phase diagrams. So if kappa is greater than 1 over square root of 2, or kappa is smaller than 1 over square root of 2, then in this case we basically just have a phase diagram like this. Oh, sorry, this is T, this is DC, this is HC, this is H, and in this case we have a more complicated phase diagram. Sorry, no. Like this. And this is DC. Here we have HC. Here we have HC2. Here we have HC1. And the HC1 is equal to phi naught over 4 pi lambda squared ln of lambda over psi. HC is equal to 1 over square root of 2 phi naught 2 pi lambda psi. And HC2, which we derived last time, is phi naught over 4 pi psi squared. Okay, so this is the phase diagram, and if I plot the magnetization versus H, then I have here HC, I have here HC2, I have here HC1. Then for a type 1 superconductor, remember that B is equal to H minus 4 pi M. So basically what happens is when I apply H, the system develops a magnetization to cancel the magnetic field, and they're just equal. And this abruptly stops at TC. But if you have a type 1 superconductor, a type 2 superconductor, sorry, then something else happens. It basically goes up all the way to HC1, but at HC1, vortices start to penetrate into the sample, and we have a behavior that looks like this. Okay? So with that, I'll move on to the next topic, which is the Josephson effect. Unless anyone has any questions about that.
You can explain again
this plot?
Yes.
So this is the magnetization of the sample as a function of H. So for a type 1 superconductor, it just goes, it's linear in a way. This is like 1 over 4 pi H. Does such that it cancels, such that B is 0. Okay, this is the Meissner effect. It's screening away the magnetic field.
Okay, it's in a type 1.
It's type 1.
Okay.
But in a type 2, what happens is that there is an abrupt change at HC1 when vortices start to penetrate in. Each vortex that penetrates in can be considered as a reduction in the magnetization because flux is coming through the sample, right? So if you measure, if you measure at the point where it breaks down and you have all these vortices inside, I don't know if you remember, but it was a bit, last time I was a bit confused, but eventually we came to the conclusion that there are vortex cores. Their typical size is psi, okay? And there is some typical distance between them, L. And as we increase the magnetic field, this distance L becomes smaller and smaller and smaller. And at the critical value, they basically start to overlap. In that case, basically the magnetic field is penetrating everywhere. And therefore, B is equal to H, and the magnetization therefore must go to 0. So you understand that each vortex that is penetrating in is allowing magnetic field lines to penetrate. So all the magnetization in this in the superconductor is canceling the field. Anytime field is penetrating through it, this is a reduction in the magnetization of the superconductor. Yes.
In superconductive state, there is a kind of vertical symmetry. It's a pair, right? There is a symmetry.
Again, in this superconducting state, there is a time reversal symmetry. That's what you're asking?
Yes, right?
Well, if we apply a magnetic field, then we broke time reversal symmetry explicitly.
No, so the question is, there is a time reversal symmetry, but in type 2, when there is a vortex, so specific in this area, time reversal symmetry is breaking?
So let's go backwards. First of all, if there is an external magnetic field, time reversal symmetry is broken explicitly. It doesn't matter if it's type 1 or type 2. Now, I think that what you're saying is that if you're deep inside a superconductor of type 1, far, far away from the boundaries, okay, you can't detect any magnetic field. You feel as if there is time reversal symmetry. Okay, that's what you're saying. That locally it looks to you like there is time reversal symmetry, but there is no time reversal symmetry because remember that there are Meissner currents going around which are screening the magnetic field.
Okay, so how type 2 remains superconductor even then?
How what?
How type 2 superconductor remain superconductor?
Remain?
Yes.
Because you broke time reversal symmetry.
Yes.
So the fact that you break time reversal symmetry, okay. I think that what your question is, okay, so why, let me ask you a question in return. Why do you think that any breaking of time reversal symmetry will immediately destroy the superconductor? What is your intuition? Is your intuition that like the Anderson's theorem or something like that?
Yes.
Okay, so first of all, I didn't teach the Anderson's theorem, definitely won't do it this year. Yuval is exactly touching on this, but the point is that if you have time reversal in odd disorder, or you have disorder and you break time reversal symmetry explicitly like we did, that allows you to break Cooper pairs. Or it creates an imbalance, in your language, it creates an imbalance between the contribution of the Cooperon, the pair scattering, and the single particle. And that will ruin superconductivity. But as Yuval can tell you, first of all, that it doesn't ruin superconductivity immediately. There's a certain strength that it needs to be. And the point is, and then, there's even another effect, which is just that the magnetic field is so large that it just breaks Cooper pairs. This is called the Pauli limit. But the point is that you'll find that in typical superconductors, this Hc2 is much smaller than the strength of the magnetic field you need for all these effects. So we're talking about very weak fields compared to the effects that you're talking about. To break a Cooper pair is a lot of energy. Okay, so just let me give you numbers. So the superconducting gap, which is comparable to TC, right? In the right units, in millivolts. So you can if you want to do like just hand waving back of the envelope calculations, then a Tesla and a Kelvin are the same, and they're both 0.1 milliV. Now TC in these materials is like I don't know, between 1 and 10. So that means that breaking a Cooper pair will take you a Tesla to 10 Tesla. Okay, more or less, just roughly speaking. The typical magnetic field you destroy superconductivity in a standard superconductor like a metal or something is sub-Tesla. It's a 0.1 Tesla, depending of course on the superconductor. If were you in the seminar we had this week by who gave the seminar this week? Muntasser. Did you go to Muntasser's? No?
Yeah,
What?
yeah.
Yael what? Yael didn't. Yael missed it. So I was talking to Muntasser exactly about that. He showed HC2 measurements, and his HC2 perpendicular. This is a planar superconductor. The orbital, this is what we call the orbital critical field. It's not spin related. What you're talking about is spin effect. The orbital critical field was around 9 Tesla and comparable to the in-plane one. So I immediately told them, look, this is a huge magnetic field. So that was an example of it. Okay, let's do the Josephson effect quickly so we can start BCS today. So, if you remember, I made an analogy between the stiffness of a superconductor, okay, and the response of a crystal to shear force. Okay? So now what I want you to imagine is that we have a superconductor. Let's call this superconductor 1. And this is superconductor 2. Okay? And in between there is an insulating layer, boundary layer. And this layer size is going to be of order delta. Okay, so this we can call this coordinate x. This will be x equal to 0. This will be x equal to delta. Okay, and delta is very small. In particular, we want delta to be smaller or of the order of psi. Okay, if delta is much larger than psi, you just disconnect these two superconductors. What is psi? Do you remember psi is the healing length? So it means that psi more or less gives you the length scale over which the superconductor decays. Okay, so we want these to be close to each other. In real materials, the way they do this, and this is an extremely important technological advancement, all these superconducting based quantum computers use this technology. They take aluminum and they create an oxidized layer on top of it by just allowing it to be exposed to oxygen, and then they grow another layer of aluminum on top of it, and you get aluminum, a thin oxide layer, and aluminum. And for whatever reason, aluminum tends to create extremely clean and uniform oxidation layers. And that creates some of the most cleanest and most high quality Josephson junctions. So this is the kind of thing we're imagining. Okay. Yeah, and what does this Josephson junction do? So I want you to imagine the same thing with a crystal. Imagine that you have a crystal, and then you have like a small like rubber, very soft material in between. Okay, and then another crystal. So if we apply shear, remember that, you know, if I want to create a gradient of the phase across, you know, x, across the direction x, it's basically like, you know, it's like I have a crystal which is fixed, right? And I apply some force F along this, and I want it to kind of tilt. Tilt like this, right? Now imagine that in between somewhere here, there is like a rubber region where it's extremely soft. So how is it going to respond? It's going to respond differently, right? It's going to look like this. It's actually going to look like this. And then I have my rubber. It's going to, you know, bend, you know, as basically as much as I want. And then it's just going to continue here. So what happens in these Josephson junctions is that you can imagine that the phase is like super rigid here compared to here. Here the rigidity goes down. How do we understand this? So if you remember the stiffness rho s is given by rho naught over 2m. Okay, this is basically like psi squared over 2m. Okay, the average psi. Now what happens here is that the superconducting order parameter basically decays here and decays here. So the average psi in that regime is much, much smaller. So the stiffness is much smaller. Okay, so this is the kind of physics we want. Now let's focus on the current that is going through this junction. So I remind you that the gauge invariant current operator, or whatever, is okay. Now let's discretize this. Okay, assuming the delta is very, very small. So we have that this is equal to E star over 2mi. Then we have psi star of 0, psi of delta minus psi of 0 divided by delta minus psi of 0, psi star of delta minus psi star of 0 divided by delta minus E star squared over m a psi naught squared. This is kind of, you know, this is not an accurate description, but this is assuming that delta is very, very small compared to variations and so on and so forth. So this thing is equal to, so what do I have here? So I have psi squared terms. I have Yeah, so what I get is this. So the constant terms cancel here, and I get okay, and now using the fact that e to the minus I e star integral from 0 to delta a of x. So again, I'm going to assume that the magnetic field, so this is x. I'm going to assume that the magnetic field is going inside. So this is z, and maybe y can be this direction. So basically A depends only on x and typically points in the y direction, such that the magnetic field no, in this case I want to take wait a second. Probably want a y to depend on x. Wait a second, let me see if this matters in any way. I guess it doesn't matter. For now, it doesn't matter. So let's write here ax dx. This thing is 1 minus I e star delta times ax of x. And therefore, if I use this expression plus, okay, if I plug this in here, then I get e star over 2m delta I psi star of 0 e to the minus e star integral from 0 to delta dx prime ax of x prime psi of delta minus psi of 0 the integral of I e from 0 to delta dx prime ax of x prime times psi star of delta. So if you open up according to this expression, you'll get exactly what you have about here. But the nice thing about this is that now this looks like now I can assume psi of x is equal to square root of rho e to the I theta of x, and we're going to neglect variations in rho, although they exist. Okay, they exist, but we're still going to neglect them. Then we're going to get that the current density from left to right takes the following form: J max sine of delta theta tilde, okay, where this delta theta tilde is what we call the gauge invariant phase difference. So it's basically the phase difference of the superconductor minus E star integral from 0 to delta the x prime ax of x prime. Okay? And this J max guy is equal to E star rho divided by M delta. Okay? So this is what we call the Josephson relation, which was derived by Brian Josephson in 1962. There's kind of a nice story about this, that he actually took a course in Cambridge with Phil Anderson. Phil Anderson gave a course. He was an undergraduate student. During the course, he asked a lot of questions. It was like a mini course about superconductivity. Hold on one moment. And he approached Anderson and asked him many questions even after. And Anderson kind of guided him until he finally came up with this equation. Eventually, he received the Nobel Prize for this. So, this is an undergraduate. So that's afterwards, I think he went a little bit crazy, but that's a different story. He started doing to study telepathy and telekinesis or whatever. Stories say, I heard rumors that he rides around, and he used to ride around Cambridge. He's now probably very old or passed away, I don't even remember. He used to ride around Cambridge with a helmet that has tin foil on it, such that people can't steal his ideas. He was looking into telepathy. And I think that if you ever see that in a show or something, he's the origin of that crazy idea. Okay. So this is, and what does this imply? It implies that if there is a difference in the phase, in the gauge invariant phase across the superconductor, then a current will flow, and the magnitude of the current is this expression. Now, this is called the DC Josephson effect. So let me say, this is DC Josephson effect. Now let's do the AC Josephson effect. Okay, so to do that, let's recall that if we take delta Sxy to delta phi, where phi is the Coulomb field or the time component of the four vector gauge field, then this gives us the equation grad E is equal to 4 pi V naught times dt theta plus E star phi. Okay? Yeah, so now if there are no charges in the system, then we basically conclude that dt of wait a second. Yes. So now what we want to do is, imagine we want to take the potential on one side and subtract from it the potential on the other side. So we want to have a bias, a voltage across the barrier. Then we'll take phi at this side and subtract from it phi on that side. So we're going to find that E star times V, the bias voltage, is equal to minus dt theta of delta minus theta of 0. Okay? Or in other words, this is what we call delta theta. This is this delta theta here. So what we conclude is that when there is a bias voltage, then delta theta that appears over there is time dependent, and it's equal to minus E star V. Plus maybe some constant, but that's just the phase shift. It's not interesting. Okay? And therefore, we need to correct that equation. So we get that J left right is equal to J max sine of, let's call it delta theta tilde of 0 minus E star V times T, where this delta theta of 0 is this expression here. Okay? Now this is quite an astonishing result. What it implies,
We should integrate over time E star V, right? It should be a T or something.
what? Oh yeah, T. Yeah, this is the same T.
Ah.
Just a mistake. So what this implies is there are a few things that are quite astonishing. So let me list them. First, the current is periodic in time. So it's going back and forth, back and forth. Although the bias voltage is constant. There's a bias from one side of the barrier to the other. But the current is going back and forth, back and forth. That's the first thing that's quite astonishing. The second thing is that the frequency is actually set by the voltage itself. So initially people thought, when this was discovered, originally people were extremely excited because they thought you could produce any frequency you want with this. Okay, there are of course limitations that come from other issues, and for example, you can't solve the terahertz problem with this. But potentially that was very interesting, so that you can control the frequency at your will. And finally, the magnitude of the current, J max, doesn't depend on the voltage. It has nothing to do with the voltage. Okay? So this is quite astonishing. We can also compute okay, I'll skip that. You can also compute the energy of the Josephson effect by calculating the power. The power. I times V. Okay, good. Okay, so this is the Josephson effect. Now let's talk about what happens when you put a magnetic field. And then let's talk about squids, and then we can move to BCS theory. So let's try and do the Josephson effect in a magnetic field, and then go for a break. Or you need a break now. אתה הולך, נכון. So, what I want to imagine now is that I have my Josephson junction is like this. This is, if you like, this is like superconductor 1 and this is superconductor 2, and this is the barrier between them. Okay? And now I have a magnetic field which is penetrating like this. So we have B equal to B times Z, and the coordinate system is like this. So this is the X direction, this is the Z direction, and this will be the Y direction. Okay? And then we're going to have A be some A of X in the Y direction. So we can make a drawing like this of what we expect. So here we have, say, 0, here we have delta, and then A is doing something like this. Oh, sorry. So here we have A infinity, and this is A of minus infinity. Okay? So A is changing. What happens is that because the magnetic field is screened inside the superconductor, then A can only vary close here. So, and what you have here is that if we look at the magnetic field, H, let's see if I have another color. Okay, never mind. Let's do it dashed. If I plot H of X, then it's basically constant, okay? And then it decays into the sample over a length scale lambda. Okay, and the currents, the screening currents, in accordance to the London equation, are basically like that. This is J.
This depends on the type of the superconductor, right?
You mean like if there are vortices?
Yeah.
Well, let's assume that we're below HC1.
Okay.
Okay. You can have that, of course, if you, but again, you have to remember that as you're going to see in a moment, what happens is that the magnetic field is going to cause phase shifts across the junction. And if you remember, phase shifts are like this shear force on the crystal. And here we have a crystal, there's like two crystals connected by an extremely soft rubber piece of material. So, and you can imagine that if you apply too much force, it just tears. Once it tears, they're incoherent with each other. There is no more superflow going through the junction.
Right.
And at that point, it becomes resistive, and there's dissipation, and all this business. So, because you see the before you start injecting what you call them vortices into the sample, you'll break this. Typically, you'll break this junction much earlier. Okay, so now let's, we can define, so, J is equal to E star times V. This is the superconducting velocity. So just taking the same expressions we had on the board before, we can say that the integral over y, so I'm doing an integral in the y direction at a given z and x, v dy So first of all, this is another important thing. So you can ask, remember that we want to screen the magnetic field. So in which direction, in order to screen a magnetic field in the z direction, in which direction are the currents flowing? The screening currents.
In the y direction.
In the y direction, right? Because if I, this is like when you learn איך זה נקרא, electromagnetism, there is this example where there's a surface with constant current in it, and it creates a magnetic field perpendicular to it. So the magnetic field is in the z direction. We want to be perpendicular to it.
But we don't want to enter to the superconductor, right?
Yes, exactly. So we're gonna have the currents going in this direction. Sorry, it's what I drew before is incorrect. If you have a current like this, then you have a magnetic field like that. Okay? So this is like right hand law. So yeah, actually it's gonna be opposite. It's gonna be like this. Right? Because then no, it's the way I drew it before. So the currents are like this, and therefore they create a magnetic field in the opposite direction. On the other boundary, they're going to flow downwards. They're going to screen. So it means that V, this guy, is basically Vy in the y direction. So now I'm going to integrate over Vy. And this is going to be an integral from 0. So let's imagine that I start from some value at 0. This is like y equal to 0. And I'm going up to some value y. Okay, so an integral dy prime. So I have here dy prime. This is y. And I have dy prime theta minus E star ay of infinity. Now, why did I write here infinity? Let's take x to be a smaller, x. Let's take x to infinity. Sorry, x to infinity. Okay, so let's say we're deep in this superconductor. So we're not doing this at the junction, we're doing this deep inside. Then what we get is we get theta of y minus theta of 0. Okay, minus E star ay time a infinity times y. So why did I go deep inside into the superconductor? Because like we said before, here because b is 0, a is constant. If a is constant, then I can do this integral easily. So what can I conclude from this? So now you could imagine that I can do the same thing on the other side. Okay? So let's call this theta infinity. Okay? I can do this on the other side. I can do this deep in this phase. There I'm going to get, or actually let's call this theta, let's call this is superconductor 2 and this is superconductor 1. So let's call this theta 2, and then we have therefore the theta 1 of y minus theta 1 of 0. is plus E star A of infinity times y. Or minus A of minus infinity, but A of minus infinity is the minus A infinity. And therefore I get that delta theta of y, let's assume that we anchor the phase difference here to be the same, then delta theta of y is just E star A of infinity. Sorry, it's what am I saying? Oh, so I forgot one last important ingredient, and that's the fact that this is equal to 0. Why is it equal to 0? Because remember that the currents decay to 0 deep inside the superconductor. We're using the fact that the current is 0 there. So this integral is anyway 0. So I can move this to the other side, and then indeed I get A of infinity minus A of minus infinity, which is just 2 times E star A of infinity. Okay? Times y. So this is times y, and this is times y. Okay? So basically it's telling me, what it's telling me is that locally, the phase difference across the boundary is now changing as a function of y. So the phase difference here, and here, and here, and here are different because of this magnetic field. That's what the magnetic field is doing. Okay? So we get that locally J of y, this is the current, is E star rho naught over m delta sine of okay, now what we need to do, so I remind you that let me remind you that delta theta tilde, right, is delta theta, okay, minus the integral x, wait a second. Yeah. X of y okay, let's go on a break. I need to figure this one out. Something I missed here. So let's take a break here, and what I'm going to show you after the break is that basically so we already saw that the phase difference across the boundary depends on where we are along y linearly, and now we want to convert that to what is the local current density across the boundary due to this phase difference. Okay?
If the height of the superconductor is huge, they are virtually disconnected.
They are what?
Like disconnected. There's like an infinite difference between the phases.
We'll see what it causes. It becomes periodic.
Okay.
Okay, but basically the larger this is, the more flux is going to come in, and it's going to create. But yeah. So yeah, what I was saying before the break was the point is that this just gives you the phase difference because A is along Y. A is pointing along the Y direction, so there is no the integral over AX doesn't give any contribution, and therefore JY, the current density across the boundary as a function of Y, is given by E star rho naught over M delta sine of this delta theta. So we just get Y E star A of infinity minus A of minus infinity. Okay, now on the other hand, we can connect this to the flux, right? Because imagine that we perform a closed contour like this, okay? And we go deep, 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 deep in. The magnetic field is perpendicular to these two things. And let's do it here along this Y, okay? So the amount of flux penetrating this thing, so we have that the integral over this closed contour dl dot A, right, is going to be exactly this difference. So it's going to be it's going to be Y times A infinity minus A of minus infinity. Right, this gives me Y. A infinity, yeah, okay. Now what this, but this on the other hand is equal to the total flux. So what is the total flux? The total flux through this region is Y times a delta plus 2 times lambda, right, times B. Okay? Yes.
Take the difference between the phase far away from the barrier, right?
Yes. Here and here, yes.
And then you take the current, but near to the barrier. So.
Yeah, you're asking about yes, that's true. Yeah, but okay, remember that first of all, remember that when we say deep inside, we just mean deep inside compared to lambda. That's the first thing. So it doesn't have to be that deep. And in any case, beforehand, when we assumed, that we have a phase on one side and a phase on the other side, that was, of course, also an approximation because, the phase changes somewhat continuously. So in the same spirit, we're neglecting this. We know that, if I look at the, if I allow myself some buffer layer, which is lambda, then the phase here has to be different than the phase here by that amount. Okay, so the overall phase difference. Now, how can you think about this? Okay, so what can variations like this change? They will diminish the magnitude of the current, because you see here we took 1 over delta, but if the effective size of this Josephson junction is actually larger, then the current it will carry will be smaller. Gradients will be smaller. But that's the overall coefficient. In any case, this is a very bad approximation. I don't care about that much. That's not what I'm after. Okay? But the point is that the total flux is basically just y times this times b, more or less, because that's the region. I'm basically assuming that
That's Stokes' theorem, right?
it's Stokes' theorem, yes. Of course, because this is equal.
This is y, this is x, and
This is equal to the integral of ds dot b, right?
Right, delta plus 2 lambda.
that's x.
What?
This is the
2 lambda, because I'm assuming that the magnetic field also penetrates lambda into the superconductor. It's more or less, it's an approximate. Actually, it's not that important, to be honest. So, so what I get, let's not call this B, let's call this H. Okay? So what I get is basically what did I want to say? Good question. Yeah, I don't know. So, okay, so I can just write the expression for J of y to be this J max, whatever it is, times sine of a yeah, so I can call this phi of y, so you can just write here E star phi of y, which is the flux up to this y. Okay, now what I want to do is I want to integrate this to get the total current. So so basically, imagine that phi total is, let's say that this size of the boundary is something like L. So phi total would be something like delta plus 2 lambda times L, right? Times A infinity minus A of minus infinity. Times H, the magnetic field. And therefore I can write phi of y times E star. I can write this basically as phi divided by phi naught times y. Okay, because in my units, times 2 pi. Right, in my units, E star is equal to 2 pi over phi naught. Okay, because the h bar is equal to 1 and the c is equal to 1 and all these constants. So basically what I get is that jy is equal to this J max sine of 2 pi phi, the total flux. Just to make it clear what I mean, this is total flux over phi naught times y. And now we can get I is equal to the integral dy over this jy, maybe times we need also some length in the z direction, so some L here, and here we do an integral from 0 to L of this dy, and when you do that, what you basically get is the following expression. You get L squared J max sine of oh wait, why is it pi? One moment. So probably I made a mistake somewhere. Okay, never mind. Let's just write 2 pi phi over phi naught divided by 2 pi phi over phi naught. Yeah. And this is the current. So what we see is that when you put a flux through a Josephson junction, then this is okay. So first of all, I assumed here that delta theta is 0. So I assume that besides this delta theta, this is 0. So this whole thing is basically the maximal current that the Josephson junction can carry. So for example, if I were to put a bias voltage here, or if I would make a phase difference, then that would create additional current which would come here. So there would be something like sine of delta theta or something like that. But I neglected this. This gives me the maximal current. And what we find basically is that this I max as a function of phi over phi naught basically has the structure yeah, it's basically like this. And people see these kind of effects. Okay? So this is very useful because you can use this to detect magnetic fields, for example. First of all, this is a very important phenomena because I can just give you an example. Recently, people discovered in 2018, when I was in MIT, they discovered that if you take 2 sheets of graphene and you twist one with respect to the other with a tiny, tiny angle, like a degree, okay? You get this super pattern, which is very long wavelength, called moire pattern. I can maybe show you even with these chairs what a moire is. This caused the reconstruction of the band structure, and extremely flat bands formed. And in these flat bands, they saw superconductivity. But to show that something is a superconductor is not that easy. As you know, for example, a year ago we had this LK99. Everyone thought that it's a room temperature superconductor, and it took a long while to prove that it was just some weird magnetic material. And we had many examples of this before. How did they prove without any doubt that this twisted bilayer graphene is indeed a superconductor? They applied a magnetic field in plane, or maybe, I don't remember if it's in plane or out of plane. I think it's in plane, but I'm not sure. And they saw these kind of patterns. And what they said is that what they're seeing is basically some spontaneous Josephson junctions that are emerging. For example, imagine that your sample is disordered. There are regions with some angle, a different angle, maybe some regions are superconducting, others are not. And in certain cases, you can have certain, narrow constrictions where it's not superconducting, and the magnetic field can penetrate in there. And when it penetrates, across this barrier, it creates these, this is called the Fraunhofer we also saw this in Math 3. Whoever studied Math 3 with me, this is like a Fraunhofer diffraction pattern. So these Fraunhofers are extremely distinctive, and they can be used to detect, you can use them to detect magnetic fields, but you can also use them in the other way to prove that something is a superconductor, because it's, one thing is that your resistance drops to zero. A thousand things can cause that. You can have like a floating contact, bad measurement, all sorts of stuff. But to get a Fraunhofer diffraction pattern like that is not that easy. And there was also like nice experiments where they used these Fraunhofer diffraction patterns to infer what the current structure across the boundary is. There are a lot of stuff that people do with this. So this is an important relation. But one of the disadvantages of this thing is that it's we have some sort of there are two kind of things that are pulling us in different directions. On one hand, for example, we might want to make the this device sensitive to magnetic fields. Like, say we want to detect very small magnetic fields. Then we want the amount of flux penetrating this this layer to be very large. But on the other hand, we need the superconductors to be very close, so it's limiting us. So to solve these kind of problems, people came up with a better device, which is actually used here in Bar Ilan in the group of Bina Kalitsky, which is the squid.
Can I ask a question?
Yes.
The JY, it's for specific I in the superconductor, right?
It's for a specific what?
I in the superconductor, right? This is not a difference between
It's
Y0 to Y.
no. It's the J across the boundary. So I remind you that in the beginning of the class, we saw that if there's a phase difference within superconductors, there is a current. This is the current from 1 to 2 as a function of where you are in Y.
Okay, so as close to the magnetic field, they get that the current is increased, right?
Well, it's not necessarily increased, it's oscillating. Basically changing. Actually, some of the current is going in this direction, some of it in that direction and back. Right? Okay. So let's do quickly the squid and move to BCS theory. So the squid geometry, we kind of enjoy both worlds. So instead of creating one Josephson junction, we create two Josephson junctions. Okay, so it looks like this. We imagine something like a ring. And here we have the first Josephson junction, and here we have the second Josephson junction. Okay? So across each one of them we have delta theta 1 and delta theta 2. Okay? So if we have a current flowing from here to here, okay? Then we know that I is equal to some I max, right? Sine of delta theta tilde 1 plus sine of delta theta 2 tilde. So each Josephson junction gives some gauge, there is some gauge invariant phase difference across the boundary, and that will give us the current. Now let's assume that we plug in here some flux phi, then we know that this flux, right, we can do a closed contour integral around the ring dl dot A. This thing is just going to be equal to the flux. Or, you know, if you like, H times A. Now, on the other hand, you know, we can assume that the phase here is very rigid everywhere. Okay? So the phase, you know, here we can have like phi 1 and phi 2. So we understand that sorry, not phi 1, let's call this theta 1 and theta 2. Then we can understand that delta theta 1 tilde is equal to delta theta 2 tilde, right, plus 2 pi phi over phi naught. Okay, so what it basically means is that as we do this contour, all the flux that is falling, all the change in A, is all happening across this boundary. Okay? So then if we plug this in, we get that I is equal to I max times sine of some delta theta minus or plus 2 pi phi over phi naught plus sine, half of that, delta theta minus pi phi over phi naught. Okay, and this we can rewrite as I max cosine of pi phi over phi naught sine of whatever delta theta you might have across these two superconductors. This is just by taking the sum and the difference. And this implies that I max now is very different. It looks like this. Sorry. Okay? So it's not decaying anymore as a function of flux. That's one thing. And also the flux that we can take in. Okay, so the reason it doesn't decay as a function of this is because we've neglected the size of the Josephson junction compared to the total flux that is penetrating here. So there is some flux, a little bit of flux that is penetrating through the boundaries, but we've neglected that. If we would zoom in on this region, okay, then we would have again these, we would have, and there would be some magnetic field penetrating. It would cause the same Fraunhofer effect, but all that we've neglected, assuming maybe that most of the flux is here, or that these are very small Josephson junctions, but we still enjoy this kind of periodicity, where this is, this is a pi. Wait a second, 0 and phi over. No, sorry, this is 1, 2, 3, minus 1, minus, and so on and so on. Is that true? No, this is 1/2. This is 1, this is 2. This is minus 1, this is minus 2. Okay. And this is, so for example, what does Bina do? Bina goes parks the squid somewhere along this. So for example, she can apply a magnetic field of her own, small one, to shift it. And she can park here. And then any small change in the magnetic field causes a very strong derivative. And she can lock in on that. So, and it becomes one of the most sensitive, she has one of the most sensitive magnetic field detectors in the world using this. So this is, and they think, you know, and there are endless applications for that. So for example, I don't know if they've been using these, but you know, maybe for example, you can detect Hamas's tunnels with this thing because it's extremely sensitive. I'm just throwing crazy ideas. Okay. And you can do many other. You can do, for example, you can. There are all sorts of technological advances, like search for metals. You know, do quality control on stuff. You know, endless. It's technologically, it's a very important capability. Okay, so now, how much time do I have left? Like 15 minutes or half an hour? Okay, so let's do BCS theory. I kind of skipped a few things like the little parks experiment, but because of time, we can, maybe I'll just let you solve the little parks in the exercise, in the home exercise. So BCS theory. So let me give you a little bit of background. So BCS theory. So everything we've done up to now was macroscope. What did we do? We took Ginsburg-Landau theory of a bunch of bosons. Okay, forget about Ginsburg-Landau theory. We had an action for bosons with interactions between the bosons. We lowered the temperature. We saw that at zero temperature they condense, they create a superfluid. That superfluid is a symmetry breaking state. A consequence of the symmetry breaking is a Goldstone mode and dissipationless current and rigidity. Okay, same thing happens to a crystal that crystallizes. The analogy exists. It has the topological defects in the form of vortices. Then we gauged this superfluid, which means that we charged the particles that are condensing. We saw that once we gauge the particles, there is no longer symmetry breaking. Instead of symmetry breaking, we got the Meissner effect. The Meissner effect means that the boson acquires a mass and the Goldstone mode gets Higgsed away. So it's very different from symmetry breaking. We don't have any low energy excitation whatsoever. Everything is gapped. Very different. And then, you know, we took this action and we looked at it in the static limit. We neglected time dependence for the most part of it. And then the action, if you neglect imaginary time dependence, becomes the Ginsburg-Landau theory. And the saddle point equations are the Ginsburg-Landau equations. And we've studied these and we saw different phenomena, type 2, type 1, everything we've discussed now, Josephson effect, that all emerges from that. But on top of all this, and by the way, this is how Ginsburg-Landau got to this. They saw an analogy between superfluidity and superconductivity. They wrote a theory for both, one of them gauged and one of them not gauged, and everything worked out beautifully. They could explain a wide range of phenomena which we've just discussed, and much more. But there was still a question that was arching over this whole thing, or like a dark cloud that sits, is what the hell, what bosons are you talking about? And this is what BCS theory comes to answer, is what are these bosons? These bosons are basically Cooper pairs. So Cooper pairs of electrons. To get Cooper pairs of electrons, we need an attractive interaction. We'll see that in a moment. But the first thing I want to discuss is what is the origin of this attractive interaction. So what happens is that if we think about the scattering process, imagine that you have two electrons entering a vertex, gamma, and coming out. So we have them coming in, K and K prime, and then exchanging some momentum Q. So here we have K plus Q and K prime minus Q. So they exchange some Q, and Q can be a 4 vector. So let's assume that it's like omega, or let's call it capital omega and Q vector. Okay, so they can exchange both momentum and energy in this process. So we need to write this in an action formalism. So in an action formalism, this would mean that the S interaction is something like maybe T over L cubed, sum over K prime and Q. And then we have this gamma Q is this vertex. Then we have psi bar K plus Q sigma, psi bar K prime minus Q sigma prime. So this can be sigma prime, sigma prime, sigma, sigma. These are the spin indices. Psi of K prime sigma prime, psi of K sigma. Okay, this is the general interaction. It's a density-density interaction, okay, where this is one density. This guy is the one density, and this is the other density. And yeah, it's kind of general density-density interaction. Conserve spin, and here the sum is also over sigma and sigma prime. Okay? Questions about this up to now? No. Good. So now, typically, this gamma has two contributions. So this process is actually the direct Coulomb scattering, okay, plus the exchange of a phonon. Okay, direct Coulomb phonon. So this direct Coulomb guy we can think about it in different ways. So naively, this guy is 4 pi e squared over q squared. Okay, which is the Coulomb repulsion. It's the Fourier, this is the Fourier transform of a 1 over r interaction. But in fact, because we're talking about a Fermi surface, there is screening. So we can take into account the screening in different ways. But let's just take this to be q squared plus q Thomas Fermi squared. This is Thomas Fermi screening. If we're talking about energies that are significantly smaller than the Fermi energy, this is a very good approximation. Any questions about this approximation? No. Good. Then what is this guy? Well, this guy is basically, first of all, let's start from the fact that this is negative. This is an attractive interaction. Why is it attractive interaction? It's a second order process. Second order perturbation theory typically reduces the energy. Okay, that's maybe one way to see it. You can also view it from the fact that you can derive this interaction by, only taking the bare Coulomb, but also adding to the interaction a coupling, say some sort of, okay, let's call it G. Let's call it G of Q. Phi, some phonon degree of freedom of Q. Psi dagger, psi bar K plus Q, psi K. And here you're going to have a sum over K and Q. And this is some general phonon mode. To be honest, you should be complaining now. Why? What kind of phonon is that? What is phi? What is a phonon even? Do you even remember, or did you ever learn what a phonon is?
The vibrations of the sound.
Right, but how do we get the phonons?
It's like acoustic.
Optical.
Acoustic and optical, that's right, but we don't actually, something that is important to know is that there are superconductors, for example lead or niobium, all these metals. The atoms, they form in a Bravais lattice. So there is no basis. What does that tell you? That there is no optical phonon. It's only acoustic phonon. Right? So lead, for example, doesn't have optical phonons. Okay, that's one thing. So I can tell you a funny story that I remember that when we were in, when I was doing my PhD, Johann Manhalt came to give a colloquium. Johann Manhalt was very, was a hotshot back then because of the LAO-STO interface. He was trying to describe their attempt to understand what is the phonon that is responsible for superconductivity in LAO-STO, and they had some, I'm guessing, I don't really remember, but they had some Raman spectroscopy experiment, I'm guessing, to compute the frequency of the phonon as a function of T, and they looked for a kink in the phonon spectrum at Tc, and he was talking about optical phonons, and all the students were like confused. They were like, wait, is superconductivity coming from optical phonons or from acoustic phonons? And then we started going through all the professors, I won't name them, in Weizmann, asking them if the phonon that's responsible for superconductivity is acoustic or optical. And it was very funny because it was like a survey. Everyone had a different answer. And I remember till now, like then I moved to MIT as I finished my PhD. I had a postdoc, and I was sitting for lunch with Patrick Lee, who was one of my advisors at MIT, and I was starting to discuss the same debate, and he was like, how is there even a question? Like, there are metals, they don't even have optical phonons, and no one even raised that point. And it turns out that even that is bullcrap, because you can have superconductivity coming from optical phonons, you can have superconductivity from acoustic phonons, they can all contribute, but we'll get to that later. But the point is that if you remember how you get your, how do you derive your, how do you quantize, for example, these phonons? You have a displacement field, U. Typically it's denoted by U, which is how much the ion is moving compared to its original position, and there is some associated momentum. So here we should have U, right? But that's a vector. A vector can't couple to density. So what is coupling to density? Do you know? Any idea how to couple?
You have to do the inner product with the lattice vector.
Lattice vector. Like A in some direction? That would break a symmetry, wouldn't it? You're saying that the coupling is only along a certain direction. So the idea is that you need to dot product it with Q. And that's not surprising because this is what we call a gradient coupling. What is a gradient coupling? So a gradient coupling is, imagine that these are the equilibrium positions of the ions. Now let's imagine that I create a gradient. So here the atom is located at its position. Here I shifted a little bit to here. Here I shifted a little bit to here. Okay? Here I shifted even more. Now I start to shift in the other way around. So I take it back, 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 something like this. So you can see clearly that the distance, see the distances here, and the actual distances between the particles are actually smaller. So this creates, so it means that if you have a gradient along the direction of u, right, u, this is parallel to u, then you get density. So when u and the gradient are in the same direction, you get enhancement of density. And this locally, for example, you could imagine that these are positively charged, they enhance the potential, they create, you know, a term like this. So this thing is typically what we call phi. It's the longitudinal phonon, and if it's a simple metal, then it's going to be the longitudinal acoustic phonon. Okay? Now imagine that we integrate out this phi thing. What does it mean to integrate out the phi thing? So remember, wait, did we actually integrate out anything in this course? I don't remember. But it's, imagine that you have another term in the action which is phi squared with some Green's function. Then we complete the square, we're going to get this, you know what I'm talking about, or am I losing you? Yeah? No. So imagine that we have, for phi, we have something like, I don't know, 1/2 phi, you know, minus omega squared plus CQ squared, where C is the velocity of this phonon. So this is like waves. This is like a low energy, long wavelength approximation of these phonons. So now imagine that you complete the square with this phi here, phi q. So what you're going to get when you complete the square is you're going to get 4 fermion interaction. But the contribution to this thing is going to be 1 over that. And that's exactly this. So what you get here is minus something like g squared divided by minus omega squared plus CQ squared in real time. But if you do Matsubara, then it's going to be plus. Okay? So what it tells you is that you basically have 2 contributions. One of them is, but let me go back to maybe imaginary time. Hold on, my kids are driving me insane.
So this is the inverse of the Green's function, the interaction.
It's the inverse of the Green's function. No, it's just the Green's function. This is the Green's function times g squared, which is the coupling.
Yeah, that's
the inverse. Yes, of course. That's always the way it is. I don't know if I've shown you this. Okay, so what we basically see here is that at very large, so how does it look like? So our interaction looks like this. If we look at the interaction gamma of Q as a function of frequency omega, okay? Then, we call this capital omega. Sorry, let's call it capital omega. Then at very high frequency, it's repulsive. Then we have some sort of divergence, and then it goes to some lower value. This is basically what happens. Where this is something like 4 pi e squared over q Thomas Fermi squared, more or less of the order. Okay? And this guy is 4 pi e squared over q Thomas Fermi squared minus g squared over c q squared, whatever that is. Okay? So this is reduced compared to that. Now, there is a whole story that if you take into account corrections to this interaction, then this repulsive part gets renormalized, but the phonon contributions, only this gets renormalized at high frequency and this not. I'm not going to get into that. This is all captured by the Ashburg theory, and we might get to that later. But the point is that if you cut yourself, and this, by the way, this is what we call omega Debye. So what do I mean by omega Debye? This is also something I need to plot. So here, let me plot the dispersion. So in general, what we really have here is omega q squared. If I have the entire, so if I plot this omega q as a function of q, then indeed close to the gamma point, it's basically linear, and then it does something like this, where this is like h, this is n, this is again gamma, this is p, and this is h, and this is the phonon, this is a niobium. This is phonon dispersion of niobium. And then we have another mode which is not that important to us. Which is this is the transverse acoustic mode, and this is the longitudinal acoustic mode. And you can see indeed that here at small, near the gamma point, at small momentum, it's linear. This is the linear dispersion of the mode that I was writing before. This is the entire spectrum, and this bandwidth is what we call omega Debye. So if I kind of integrate over angle, then typically this reduction, this resonance, is now going to get smeared into something like that. Okay, it's smeared also because it's damped. I'm putting that aside. But the typical frequency at which this happens is omega Debye. Omega Debye is the bandwidth of these phonons. When you're much higher than omega Debye, nothing happens. When you become much smaller than omega Debye, most of the phonon density of states already contributed and reduced your interaction. And if you take into account the renormalization of this due to high energy effects, which I'm not explaining here, then basically this interaction looks like this. So you get this kind of attractive interaction, and the attractive interaction is below omega Debye. So what BCS in the end proposed, which was brilliant, because they didn't understand all this when they wrote their theory. They didn't understand exactly how this renormalization works, was an effective theory which lives in this energy range here with an attractive interaction. So they basically, let me write down the Hamiltonian. So they wrote down a Hamiltonian like this. H is equal to a sum over K. Let's write it like this. Epsilon K smaller than omega thereby. VF K minus KF C dagger K sigma CK sigma. And then you have minus V over L cubed sum over K and P, or let's write epsilon K and epsilon P, both smaller than omega thereby. C dagger K up, C dagger minus K down, C minus P down, CP up. Okay, so what is this? Basically, we're talking about some dispersion relation. The Fermi energy is here. This is epsilon Fermi. This is K. This is KF. And we're focusing on a small window of energies of order omega debye, up here in this window. In this window, we can linearize the dispersion. This is this linearization that you see here. And everything away from this energy, we've basically integrated out all of these degrees of freedom. That's how we renormalized and created this attractive interaction. So it's really an effective theory that takes into account only these excitations here. Anything out, we've already integrated out. No need to discuss them. And then within this, effectively, the interaction is attractive. Now on top of that, BCS only focused, if you remember the interaction I wrote before, it had three momenta. It had K, K prime, and Q. Okay? But because we're talking about a Fermi surface, this is a Fermi, this is like KY, KX, and here we might have Kz. Because this is a Fermi surface, we're actually only focusing on a window you see there's a width here, which is this width. We take down these lines, same thing here, around the Fermi surface. So this is this window here. And this is a very thin ring, because omega debye, the phonon frequency, is much, much smaller than epsilon f. In fact, epsilon f in a typical metal is 10,000 to 100,000 Kelvin. And the debye frequency is of the order of 200 Kelvin, 300 Kelvin. Okay? So that means that there is somewhere between 2 to 3 orders of magnitude at least between the two. Okay? So it means that omega debye over epsilon Fermi is of order 10 to the minus 2. This is called the Migdal parameter. Okay, it's very important to control BCS theory. Okay? And that means that this layer here is very, very thin across. And therefore, in this limit, you can basically have only 3 types of scatterings that are important. Okay, so if you take a particle here, say this is K, and this is K prime, then basically you can either just have density-density interaction, where you destroy a particle here and recreate it, destroy a particle here and recreate it. That's like density-density interaction, and that's it. You can have the exchange, where you destroy a particle here, create it here, and destroy a particle here and create it here. That's exchange. Both of these modes are irrelevant to superconductivity. They're marginal in a Fermi liquid. They remain unchanged, and they can renormalize all sorts of parameters. But besides that, they're irrelevant. But if K prime and K are exactly antipodal, they're like opposite. So you have K here and minus K here. Then there is another type of interaction which allows for large exchange, where we scatter this pair to some p and minus p. The name of the game is that you have to stay within this thin layer. And needing to stay in this thin layer limits by a large amount what kind of scattering events you can have. And this is called BCS scattering. And this is captured exactly by this Hamiltonian. What this Hamiltonian is describing is that. Now on top of that, we're assuming here a scattering between up and down and up.
This is only of S waves, right?
Yes, this is exactly this. We've even simplified it further by assuming only S wave scattering, and the scattering is only BCS scattering between K and minus K and P and minus K. So I see Einat is already packing, so maybe it's a good time. It's okay, it's okay. So maybe it's a good time to stop. Okay, and we'll continue next time. We'll solve this Hamiltonian, and we'll see that for any attractive interaction, we always have an instability to a paired state. This paired state is the superconductor, but this view will give us additional excitations that are not captured by the Ginzburg-Landau theory, which are the Bogoliubov quasiparticles. They're fermionic excitations. And by that, we'll obtain a lot of other properties of superconductivity. Okay? Right. Actually, אתם יכולים לעזור לי?
למה אתה באתי עם שתי מקבוקים?
לא באתי עם שתי מקבוקים. הבאתי את המקבוק הזה ביום שישי ושכחתי אותו. ג'יש.